to the last morning session of this conference. And the first speaker is Özgür Akarsu.
Thank you. Great.
And he will tell us about recent updates on the science which in Lambda CDM Cosmology.
Okay, thank you very much. Okay, so let me do this. Usually I am not able to complete my talks. Okay, then let me give the conclusion in the first place right now. Okay, so it seems that we need to consider a third accelerated expansion phase of the universe around Z1.6. In that case, it seems that we can take care of most of the tensions we are dealing with. So I will skip these parts quickly. So the idea starts with graduated dark energy. Graduated dark energy. So from Bianchi identity, we get conservation equation. So we usually use this equation, but we have another equation from Bianchi identity, which is momentum conservation corresponding to Newton's second law of motion. This is spatial gradient of pressure, and this is for acceleration. So here, so we do not see this equation in our works, because when you use observational space-time, this becomes zero, this becomes zero. We never see this equation in our works. The term in front of for acceleration is var rho, corresponds to P rho plus P, which is inertial mass density. The idea was this: maybe inertial mass density is more fundamental than energy density, because inertial mass density of vacuum energy is exactly zero. So if you want to look for deviations from vacuum energy, phenomenologically, simplest idea may be to consider it non-zero, a constant and fit to the data. We did it. It doesn't work very well, but when we go for the simplest dynamical deviation from zero inertial mass density of vacuum energy, then we can use this function to describe such a deviation. Then when we solve this equation using local conservation equation, we get this rho, this behavior. So depending on how you are choosing the parameters, this function can be written like this. So you see this function changes sign at a certain redshift. And then when it changes sign by passing through rho 0, then it exhibits a singularity in equation of state parameter, because rho passes through 0 and P is finite, pressure is finite. So when we fit this model to data, okay, this lambda, lowercase lambda, determines how this transition from negative energies to positive energies will take place. It's about rapidity. When we fit this data, this model to the data, if the transition is fast enough, we find a new region. So this part is Lambda CDM Cosmology, standard model. So if the transition is not fast enough, so we should be looking for something new around Lambda CDM. But if the transition is fast enough, then we find another region where the parameter, the constants become very stable. So this corresponds to sign change in energy density around Z2. Okay, so for standard Lambda CDM, we see this part, but for this region, we see the behavior of dark energy is like this. So changing sign, it's positive today. It is negative in the past. And the key point is this: it is negative, but it's almost exactly the same negative of the present day value. So this is, so then the thing is this: instead of looking for new cosmology around this region, we could look for it around this region. Then from this figure, you can see that an idealized model could be that cosmological constant is rapidly changing sign around Z2. So, but this negative dark energy, there were some other indications in favor of negative dark energy already in the literature. I will go through them very quickly. Oops. The first one is this Bose collaboration paper in 2014. So you see, for Z larger than 1, they were telling that in this paper, maybe there should be negative dark energy in the past. Okay, so you can see that, so cosmological constant, that you can come here for negative cosmological constant. So there's another paper here from brainwork models. So you see there is singularity in equation of state parameter. So these are related because if rho is passing to changing sign, then the equation of state parameter should exhibit singularity. So this is also related to negative dark energy. So we have another paper. I'm just showing some key papers. You see equation of state parameter is trying to get large negative values. This is understandable. I see this as a signature for negative dark energy because if we are doing non-parametric constraints using equation of state, it is almost impossible to catch this behavior. But you see, it is trying to have negative dark energies. You need to have a singularity in equation of state parameter. So it goes like that. So there are other papers in the literature. So one of the earliest papers about it here, you see around 1.5. Again, we get negative energy density. There's this paper, omnipotent dark energy. Why we call it omnipotent? Because this dark energy is able to do all kind of crazy stuff. But when you constrain it, again, we see that data prefer sign switch in energy density around 2 again. So this paper is important because, you know, for the one of the suggestions for addressing H-naught tension is interacting dark energy models. Here we studied without introducing any interaction kernel in a model independent way. We studied interacting dark energy models, but even in that case, data prefer negative dark energies for redshifts like around 2. So, okay, the point about these works is that in all these works, we see negative dark energy basically because of Lyman alpha data. Okay, so this was first observed in Bose correlation paper in 2014, but now, so let's see what's going on recently. So here again we see it. Okay, so DESI 2025, 24 and 24 here. So this paper, you see, even DESI, this is not because of new DESI, prefers favor negative dark energy for around Z larger than 1.5. This paper appeared on arXiv just yesterday, I guess. So again, from DESI, you see data prefer negative dark energy. So the thing is this, this story started with Lyman alpha, but still with DESI it is there. Okay, so what's going on in sign switch? As a limiting case of graduated dark energy, so you can assume that the cosmological constant is switching sign very rapidly. So you can describe it easily with signal function. Okay, then because the DMZ star should be almost fixed for the cosmological models, which are not altering anything in the pre-recombination universe. So if you fix this, because of negative dark energy, HZ will be smaller compared to HZ of Lambda CDM in the past for high redshifts. To compensate it, because it's an integral, HZ at low redshift should be large to satisfy this value in the DMZ star. So from this preliminary analysis, we see how H0 is changing depending on Z dagger, and we see if Z dagger is around 1.7, this curve reaches shoes measurement. And at the same time, so we see the predicted observed magnitude for supernova catches the shoes measurement value. So a potential model is able to take care of both H0 and MB tension. So for that reason, we constraint model using Planck-only data. Indeed, as we expected, we found this green curve you see here. So you see if Z dagger is around 1.5, so you get 74. So then in this work, we noticed that with this also S8 is getting smaller value. So it shows that the model is able to take care of both H0 and S8 tension and also MB tension. So, but the problem is that when we include bare data, So we see when we include bare data, model still fits to data better than Lambda CDM, but it is not able to give large H0 values anymore. So for that reason, we have another paper, improved results. So instead of full bare data, we also consider phantom data. So when we include phantom data, we see we are able to constrain Z-dagger even better. So in all the cases, Lambda CDM fit the data better, but when you use full bare data, model is stepping back. Instead of predicting like 73, it predicts 70. So we want to understand why it's happening. Then we check many tensions here. So we use phantom plus, Lyman alpha, MB prior. So you see Lambda CDM removes all the tensions. But when we include full bare data, it still reduces the tensions, but it cannot resolve all the tensions at the same time. So we wanted to understand why it's happening. When we had a closer look at the tension with each of the bare data, we noticed that it is the reason for this worsening is because of low redshift bare data, and particularly galaxy bare data is creating problem for the model. So then the next step, then instead of using 3D bare data, we could use 2D bare data, which is less model dependent. So you see constantly using Lambda CDM and Lambda CDM. Both models are exactly Lambda CDM, even at low redshifts. So for that reason, when you constraint model using only bare data, 2D bare data plus BBM prior, we get exactly the same contours for two models, but the blue contour is for Lambda CDM. This black one is for Lambda standard model. So the interesting thing here is this, when we combine Planck and 2D bare data, the intersection is fitting exactly to the Schu's result. So bringing tension to 0 sigma. So, and what about S8 tension? Thanks to Marika, she helped us to do constraints using KITS data. So we see here, so this is Lambda CDM. There is like 3 sigma tension with KITS data and Planck data when you assume Lambda CDM. In Lambda CDM, you see this contour for Planck just injecting into S8 contour, then resolving S8 tension. So then here are the results. So you see when we use 2D bare data, so the model predicts when we put all the data together, Phantom plus, KITS, bare, 2D bare, CMB, this is what we found. So this is where there is no KITS, so model works very well when we don't use 3D bare data. So here you see the chi-square difference more than 40, and Bayesian evidence is like 20. We don't have any H0 tension, there is no MB tension, there is no S8 tension. So this table I wanted to show. So I know, as Ruchika mentioned yesterday, when you use 2D bare data in any cosmological model, you'll get larger H0. We know that. But we constrained it here. You see, indeed, when you use 2D bare data in Lambda CDM, the tension reduces from 4.8 sigma to 3.87 sigma. It is true, you are increasing H0, even in Lambda CDM, if you use 2D bare data. But still tensions here, like 4 sigma. Okay, and also let's see S8 tension. So S8 tension indeed reduces from 3.1 sigma to 2 sigma when you use 2D bare data. It is true that using 2D bare data will help other models, but you should see this when we use 2D bare data. Here H0 tension is like 0.2 sigma, almost not exist. And look at S8 tension is 1.2 sigma. Okay, when we use full data, you see H0 tension is almost 0 sigma. H0 tension and S8 tension is, I'm not able to see from here, is 1.1 sigma. This is H of the universe. When we compare the H of the universe from all these global clusters, we predict exactly the H of the universe we obtain astrophysically. The model predicts that. So here you see comparison of two models. you see the contours. I mean, there's a bit overlap when you consider baseline free parameters, but when you look at the derived free parameters, you see the difference here. So they are detached. Okay. So this is when we add more data sets. So you see the contours are dancing in different directions. But when you use the Lambda CDM, when you put more data, contours are not even changing. So they're very stable. So this is like, it means that when you use 2D bare data with Keats, Planck, you have a great concordance. Okay, so then the criticism to this model since last year, in the last 1 year, is one of this. So if yes, cosmological constant is changing sign, this is a huge event, right? It should be doing something to structures in the universe. Then we investigated what's going on with the structures. If you had such a huge event around 1.7, we investigated that if you use simplest abrupt Lambda CDM, so you have a type 2 singularity in the model. But it is only in the extreme case of Lambda CDM model. So using signal function is the most extreme case. Only in that case you have type 2 singularity. Even in that case, then we investigated, even if that case, if something is going on or not, then we look for it. So if you have smooth transition, you don't have this singularity. Then what we learned from this, even in the most extreme case, bound structures are not affected from this switch. They are unsafe. So we showed this in this paper. Then the other criticism is, this is a very weird thing, right? I mean, so you have a negative energy density, and it is climbing a potential. This is not something we expect physically, right? So this was, we took a lot of criticism because of this. How can you do this, produce such a behavior from fundamental physics? And in the last 6 months, many papers are coming out realizing such a scenario. I will show only 2 of them. One is this string realization of Lambda CDM. So this is a theoretical paper, and this is observational paper. So this is the potential before transition. Then because of cosmic forces, the potential is jumping up, then becoming this in the interface. So, but the thing is, if you realize from this string realization of this Lambda CDM, what happens? I mean, the N effective should be slightly different. That N effective is 0.25. So in the observational paper, the authors constraint the model. You see this is Lambda CDM and Lambda SCDM, the standard Lambda SCDM, and Lambda SCDM plus is slightly theoretically coming with slightly larger N effective. They constraint it, so you see the results here. So and sigma 8 is this. You see sigma 8 is larger because negative cosmological constant is enhancing structure formation, but because H naught is larger, then sigma 8 S8 becomes smaller. So in any case, this model also is taking care of S8. Another theory, me, Eleonora, Antonio De Felice, and Rafael, Emre, I mean, as a team, Alberto is here. We developed this theory from type 2 minimally modified theory called VCDM. So this model is called Lambda SVCDM. So now we have a Lagrangian. So there's an auxiliary scalar field. If you look at this equation for rho phi, contribution to the Friedmann equation is given by this equation. If you solve this equation for constant rho, you see the potential is a linear potential. This is very interesting because this shows you that you don't need to jump in the potential. Even if the potential is rolling down, you can effectively jump, rho phi can jump. It is, so what you can do that, so you'll have a scalar field rolling down. At certain point, let the slope is changing instantly. If slope changes, then cosmological constant here, this rho phi will jump from negative value to positive value. So putting this condition, you are getting this function. But you don't have to work abrupt version. So this is the standard lambda CDM. So the potential is rolling down. The slope, only because slope is changing, you are getting jump in the cosmological constant. You can make it smooth by using blended functions. So now you have smooth transition. You see the potential is jumping, but smoothly. So you don't have type 2 singularity. So, or you can choose how lambda CDM is changing, like tangent hyperbolic. So you will have this potential. So there is agitated transition. So you see the potential is climbing up. This is what you can do in general relativity, but this you can do in VCDM. So we constrain this model. Again, the interesting thing here is this. I won't go to details. When we do this, we could put constraint on Z-dagger even only using CMB data. Okay, so you see the results here. So, and let me show you this behavior. This is important. Hz over 1 plus c, which is a dot, speed of the universe, is jumping here. So the universe, here, this is our current present day accelerated expansion universe. So around this point, around 1.7, there should be another accelerated expansion phase. So, but it doesn't mean that Hz is increasing. Even Hz is decreasing, Hz over 1 plus z can jump. So this is real acceleration. This is a dot, this is a dot over a. So you see it here also that if you have smooth transition, so you see there is a transition from negative ds vacuum energy to ds vacuum energy smoothly. So let me finalize with this last paper. So here we studied extension of both lambda CDM and lambda SCDM, allowing an effective to be free parameter and total neutrino mass to be free parameter. So good thing here is this, okay? So when we allow the neutrino properties to be constrained from observational data, okay? So here are the results. Let me show you. Okay, so 3 points. So if an effective is free parameter in lambda CDM, you can get H0 consistent with Schu's measurement, but the price will be that you will deviate from standard particle physics. So you see an effective is 3.5. Another thing, in that case, the total neutrino mass becomes less than 0.06 eV, which is not good, because for neutrino mixing, the mass, total mass of the neutrino should be higher than this. Okay, so but when you use lambda CDM, constrained with the data, what you predict is what we know from standard particle of physics. So here see, when you use only Planck data, so H0, S8, an effective helium abundance, supernova absolute magnitude, you see these dark colors are for lambda CDM. You don't have any tension at all, but lambda CDM plus free and effective neutrino mass, still you have tensions. When you add BAR data, so S8 tension does not exist, but we are not able to address H0 tension anymore. When you added BAR 2D BAR data, both models are doing better, but when you add Phantom plus Schu's, you see lambda CDM removes all the tensions, while lambda CDM standard model is having tension in many parameters. So thanks for listening.
We have time for one very short question.
If the lambda you're referring to is the same as the cosmological constant that comes as a result of the integration constant. If lambda is the constant of motion, integration constant from the Einstein field equations, the same lambda, right? Why would it suddenly?
It depends on the theory. Sorry?
Why would it change its sign at some point evolution history.
Why it shouldn't?
Yeah. What's the foundation?
Why it shouldn't change sign?
Yeah.
Why it shouldn't? This is my answer.
It's a constant. It's a constant.
We call it constant. We say it is science switching cosmological constant. So
it's like the speed of light suddenly changing sign.
So that is the point. Okay, now you can realize such a behavior in string theory. Okay, so in this you can see here. Okay, display. Okay, so it is not easy thing, but via Casimir forces you can uplift vacuum energy from negative values to positive values. So don't take it as a constant. It is vacuum energy. Okay, so it is jumping. You can do it in string theory, and you can do it in also type 2 modified minimal gravity. So it's possible, and you don't have to think it as like Einstein, right? I mean, so. Yeah, but then we shouldn't call it. And also, I showed here only two theories. There are other theories on archive and coming out, and Nihan will talk about we can have such behaviors effectively in f of t gravity. And last week a paper appeared on archive realizing such a behavior from biometric gravity. So the point is this. I know this is weird, okay? I mean, so you have negative cosmological constant, let's say vacuum energy, it is then climbing up. This is unexpected, but the point is this, we haven't looked at the current literature with these eyes. When we look at the current literature, re-look at the current literature, for instance, f of t gravity, you may immediately find that you can realize such behaviors in f of t gravity. I mean, this type 2 minimally modified gravity is not a new theory. It is like present like 4 years ago. Then we talked with Antonio De Felice. Then we noticed the model is able to do this. We have to look at the current theories with new eyes. Then we will see that it is easy to do this. Okay, it is not that much crazy idea. Okay, I was thinking that it is crazy, but now I believe that no, it is everywhere. Okay, thank you.
So thank you again.